So it has been a while. Thank you for the invitation here. It's been a while since I have been on the last EPIC meeting. I remember roughly 1.5 years ago, there was some, and we were 10 employees. Quix Quantum has evolved since then. We are roughly 40 employees, meanwhile, with offices in the Netherlands. Still, the headquarters is in Enschede, but we have also offices in Amsterdam and in Germany and in Stuttgart, where I'm currently here, and in Ulm. And brand new, we also have a new letterbox in London to have some activities in UK going on. Topic for today is more or less Quo Vadis photonic quantum computing, where we are and what you as EPIC community can do for us. And so far I've heard the right buzzwords: fiber coupling, single photon sources. That goes into the right direction. These are indeed the challenges that we have. And our vision is to build a universal error-corrected quantum computer until 2027. So the demonstrator should be ready until 2027. And it's really not about the number of qubits. It's not about if it's 8 or 64 or 128 or 1,000. Photonic quantum computing is the only platform where the information carrier actually is moving. So we have trapped ions, neutral atoms, where the qubit is more less located statically in a trap or under vacuum or wherever. Here, encoding information into photons is a quite nice idea because that scales very well. You can see already this nice rendering on the left-hand side is a 64 qubit system. And if you count carefully, you will find 64 of these yellow light guiding fibers that go to the core processor, which is in here. A few pumping lasers. So as mentioned from Toptica, lasers are, of course, the core pumping element here in the photonic quantum computer. We have cryostats for 2 to 4 Kelvin, where the detectors are in, some control electronics, and that's it more or less. Most of the technology operates at room temperature, unless the detectors, the SNSPDs, are still under cryogenic conditions. But it's only 2 to 4 Kelvin, not 20 millikelvin, if you compare it to superconducting qubits. And that's in principle the modular approach that we at Quix Quantum are taking. The core element is the processor in the middle that can have multiple architectures, but it's a huge interferometer where photons can interfere with other photons. A few components are not in the sketch here. Of course, we have delay lines and we have phase shifters, which is indicated by these gold brackets that you can see. So everything our photons should do is change their phase and interfere with each other. And you can show from that you can build a universal quantum computer out of this ability to interfere and to change the phase. So the processor, that's the product that we are selling since 2019 when the company was founded. The detectors we buy, so it needs SNSPDs, and there are great companies across Europe where we can source these SNSPDs. And these are indeed under cryogenic operation and conditions. We think a quantum computer in photonic will always be modular. So you will find a lot of fiber interconnects here. And we don't have a big problem with fiber connections because we are using silicon nitride. Moreover, we use a very specific mixture of silicon nitride. We use triplex. These are 2 layers of nitride and a layer of oxide. And by changing these dimensions, we can adapt the refractive index of our material so it fits very well the refractive index of a light guiding fiber. So per definition, or in this case, due to these tailored specifications, the coupling losses can be quite low. And if you then introduce also tapers at the end, then you can also match the mode of the fiber and the chip. So we follow this modular approach because we think it's the best scalability. And the bottleneck is on the left-hand side. And these are the photon generators. And as mentioned before, they are quantum dots, they are down conversion sources, and they are so-called squeezed light sources. These are the 3 different types of sources. Quantum dots and down conversion or heralded single photon sources usually create single photons, and you go for dual rail encoding or other types of qubit encoding, whereas squeezed light generators produce a bunch of photons where you can, in principle, do better error correction. So in theory, you can do this. So there's plenty of room for the sources. And indeed, This is currently also the bottleneck. This is just one very, very basic example for how a quantum computer completely based on photonics work. You have all seen the gate-based model from superconducting qubit quantum computers or ion-based quantum computers. And what we actually do is we create a big cloud, so-called cluster state of entangled photons. And entangling photons you can do just with a beam splitter. So this is why we have so many beam splitters on a processor, honestly. So this is for creating the entanglement. Then we have the ability to delay at least one channel or multiple channels, and when we can delay by one clock cycle or multiple clock cycles such a photon, and then send it back to another beam splitter. And therefore, we can do also entanglements over different clock cycles. And that becomes a very complex cluster state then. So for a 1,000 qubit calculation, we don't need 1,000 input ports. We can also use 100 input ports and just add 10 times a time multiplexing. And this has been indicated by these yellow fibers below the chip. So at the end, we can take a few photons off and entangle them with the next clock cycle of photons coming. And this is a quite mighty trick in photonic quantum computing, where you can save a lot of hardware in the end. So the steps for doing calculations on a universal photonic quantum computer are: we create this large entangled cluster state, we apply at the end single qubit gates, and depending on the measure of these qubits, we have to make decision and change the value of a few phase shifters. And this is called fast feed forward. This is the second really fundamental ingredient that you need for a photonic quantum computer. You need the sources, the interferometer, and then at the end, these fast feed forward. And depending on the measurement, you change more or less a few phase shifter values and then go ahead. And this architecture is quite, quite convenient, because the main and dominant error is not really dephasing, decoherence, or noise, it's photon loss. And this is something that you can detect quite easily. In the end, you will just figure out that a few of your photons are missing, and then you can repeat either a gate operation or measurement and go ahead. The clock speeds are very high. A few hundred megahertz. I mean, if we ask Toptica what the repetition rate of their fastest laser is, we end up in the gigahertz range. So you can have these clock cycles of photons coming in here very, very fast, and also repeat a few operations. Where we are and what actually the current challenges are. So we have the chip. This is a product since a few years, and we have sold, I think, 15 to 20 are out in the world, in Europe, mainly research institutes, and you can more or less build your own quantum computer out of it. It works at room temperature, and the fiber coupling can be done by butt coupling. So this is quite nice. Still, there's room for improvement, and I'm really curious to see the talk from Microalign later on, what the latest development is in terms of fiber coupling. So this is good, but can be better. Also, control electronics is a point that can be even faster, but there are good parties to cooperate here in Europe. Phase shifters is a different topic. So currently, this processor that you're looking at is working with thermal phase shifters, up to 50 kilohertz switching speed. And we would need for the fast feed forward faster phase shifters. And there are activities, we are also involved in a couple of them, in introducing lithium niobate, barium titanates, or aluminum nitrides or other materials into chips. Also, PZT is an option, so piezoelectric and electro-optic modulators would both work for us. We are following up some routes there in parallel, but it would be nice if someone of you has new developments, further developments on fast phase actuators, would be nice to get in contact. So this is still an ongoing topic of R&D. So in 2020, we presented the first processors, these standalone boxes, where you can build your own quantum computer. If you have the ability, if you have the sources and detectors, this is more or less the Arduino in the middle that you need to build your own photonic quantum computer. In 2023, we built our first special purpose quantum computer. It will be cloud accessible soon. So this is just the processor plus sources and detectors in a nice 19-inch cabinet. And the power consumption is also very limited. It's mainly the cryostat for the detectors that you need. The processor itself, since it operates at 20 to 40 Kelvin, doesn't need that much power, honestly. So this is nice for data centers, just to put it aside next to their HPC. And these are activities that we are, for example, performing with QMware. So they will deliver an HPC. This will be directly next to this 19-inch rack. And yeah, the ultimate target is 2027, 2028 to have this universality, that actually a photonic quantum computer is able to deliver solutions for all kind of industry sectors and all kind of quantum application, running Shor's algorithm, Deutsch algorithm, you name it. And this will also have cloud access, this demonstrator. So this is the target where we're actually heading. I'll keep this a bit short, that there's room for questions. We have a great cooperation, great ecosystem here. There are a few locks here. So some of the partners I cannot name, but in terms of integrated photonics, we are working together with Laonix, Mesa Plus Institute, Phix, Pixel Photonics, and some others, which are under NDA. Software development, there's also a great ecosystem here in Europe, QC Design, QSoft, Quantify, to name only a few of them. Then platforms, QMware is our test customer for our cloud system. And of course, we are within the quantum computing initiatives from the German Aerospace Institute, from the DLR, where we are working on the first universal quantum computer. So, and we are in EPIC, in QPIC, in EFAM, QBN, and in QFOT, of course, as industry networks. Now, how was it called? The EPIC question. Let's start with what we offer. We offer quantum as a service. So if you have the interest in doing quantum computations, you can have access to our boson sampler this year. Also, we have rental systems. If you want to have a demonstrator in your lab, you can rent a processor, you can buy such a processor. Meanwhile, institutes also buy the processors to have a lab on a chip. So since this is a universal interferometer, you can do all kinds of quantum experiments on the chip. So instead of buying 2,500 beam splitters, you can just buy a processor. That's quite convincing some quantum optics professors currently. Components. So you can buy the processors, you can have it for loan, and also some demonstrators for single photon sources. We would be interested in collaborations. We are also active in standardization of the software stack for quantum computers, and on the roadmap, everything we need for the universal quantum computer. Since we are fabless, that includes a lot of components from fiber connectors to 19-inch racks and so on. So what EPIC can actually do for us, we are highly interested in assembly and packaging, especially mentioned a few times, fiber coupling of single photon sources. Every photon counts because it's information loss. And I have to pay this information loss with an overhead in sources. And this is really my pain point. So it's not that I cannot leverage this loss. No, I have to buy it, or I have to compensate it with a lot of overhead in sources. So that is really what makes the effort here. We are interested in use cases for photonic quantum processors and computers. So if you have a use case for an universal interferometer, let us know. High-speed electronics for electro-optic modulation is on our shopping list, as in SPDs for sure. High-speed ultra-low loss modulators, especially for photonic integrated circuit integration. This is something we are working on, but we are open to alternatives. There are plenty of ways how to do this. We have 3 or 4 under investigation, but feel free to contact us. And high-quality components, as mentioned before, and of course, inspection of PICs. And that was, I think, the last important slide. I will keep it short and leave some room for questions.